It's streaming now.
Shall I start?
Yes, yes.
Shall I begin my talk?
Yes, Varun, yes.
Okay, fine. So yesterday I spoke about dark matter and the importance of, the fact that the universe, a third of the density in the universe was consisted of dark matter. But the even more surprising thing is that about 2/3 of the universe consists of a completely new component called dark energy. And the source of this component, dark energy, we don't know yet what it is, right? We don't know what it consists of, right? We still don't even know what dark matter consists of. But dark energy is singled out by the fact that it has a negative pressure. So here's a pie chart I showed you yesterday. You see that a large component of the universe has a negative pressure, and normal matter consists only of 4%. Dark matter is assumed usually to be pressureless so that it can cluster and form galaxies. Now, the dawn of dark energy began with two very famous papers, right? One in ABJ and the other in Astronomical Journal, right? 1998, 1999. And these two papers, the essence is summarized in this News and Views article in Science, 30th of January. And it tells us that exploding stars point to a universal repulsive force. So let me read this out to you. It's so exciting. The universe could be permeated by a large-scale repulsive force. The reservoir of energy fueling that force could be anything from a quantum mechanical shimmer in empty space called the cosmological constant to even more exotic possibilities like X matter and quintessence. And you see, these results, which pointed to an accelerating universe, to a repulsive force, were based only on a total of 40 distant supernovae. Right? And the error ellipse was something like this, and it firmly pointed out that the universe is accelerating. So let me remind you that now the number of supernovae has grown enormously, and it's over 1,000. And these observations have held up. So people were startled by this enormous discovery, and theorists like Mike Turner said it would be a magical discovery, right? What it means is that there is some form of energy we don't understand, right? So it was true of 1998, and this statement is true 20 years later. It is there, and we still don't understand it completely. And I should add that this discovery was given the Nobel Prize in Physics 2011. So what are these strange objects, supernovae? You all know what are supernovae, right? When a massive star goes boom at the end of its life, it explodes, and a stunning amount of energy is released, right? This energy released is, primarily in the opticals. You can see this object, right? And here is a supernova, and you can actually compare it at peak luminosity to the central region of a galaxy. That's how bright it is. And since it's so bright, you can use them to calibrate the universe at large distances. So here I'm summarizing what we know about supernovae, the stuff that is relevant for cosmology. So supernovae are amongst the brightest objects in our universe, right? Type 1a supernovae can be used as standard candles, right? This is very important, the standard candles. Over 1,000 supernovae have been discovered, redshift close to 2. And the important thing here is that distant supernovae are systematically fainter than they would appear if the universe was decelerating. Right? I'll explain this later. And this effect, this faintness effect, cannot be accounted for by light absorption in an intervening dusty medium. Therefore, the dimming of light from distant supernovae must have a cosmological origin. Right? And the implication for this is that the universe could be accelerated. Okay. So what are supernovae, right? Well, the important thing is that we still don't know exactly how a type 1a supernova goes off, right? We still don't know. Right? It's believed that it draws companion from a large star, spirals onto a white dwarf, and it explodes. but this is still hypothetical. The important thing that we know empirically is that brighter supernovae take longer to fade, right? So, you have supernovae which are, intrinsically less bright, and when they go off, right? So this is a light curve of a supernova. Here's when it goes bang, and this light curve goes up, and then it gradually declines. And the important thing, and this was noticed by Phillips, right, I think in the 70s, is that there's a correlation, right? The lower the peak intensity of the supernova, the steeper is the decline, right? So you can actually use this, you can apply a stretch factor here and convert all of these into a single template light curve. And this is called standardization, right? And this can be used to determine the absolute magnitude of the type 1s. Namely, you observe this time of fall. It's about roughly 20 days, right? And then you compute what is this value, the peak. All right. So, just to brush up our knowledge of supernovae, there are different types of supernovae, type 1 and type 2. We are interested in, and type 1 further can be divided into 3 classes, A1A, 1B, 1C, depending on what is seen, which lines are seen in the absorption spectrum. And 1A is important, right? 1A is important. The type 1 supernovae don't have hydrogen in the spectra, but the type 1A has a silicon absorption line, right? And this is very important. This is the one that is used to determine how the universe is expanding. So what's the theory here? Well, the theory is very simple. The flux of light from a distant object which has a luminosity L is given by the simple flux law, F is equal to L over 4 pi r square. So 4 pi r square can be thought of as the area of a sphere, surrounding this source, a light bulb or something, right? So if you now know L and you know F, you can determine R, right? So suppose there is a light bulb shining, in a distant place, say on top of a mountain, and you can't get there, right? But you want to know the distance between you and the top of that mountain, right? How do you do it? So if somebody tells you, hey, that light bulb is 10,000 watts, then it's great. You have something, a CCD or whatever you want to read the flux. You divide L by F and you get R. Exactly this relation applies to the expanding universe, but with a very important modification. And the modification is that this R, since the universe is expanding, is no longer a coordinate. It's no longer R because, remember, R is being stretched, right? Instead of this, you have something called the luminosity distance, D subscript L, right? And this quantity is beautiful. It's a very fundamental quantity because it's related to the integral over the Hubble expansion rate. And let me remind you, that the Hubble rate, right, has a contribution from all the densities in the universe. Right? So you have baryons here, radiation here, dark matter, and if dark energy exists, also dark energy. So all of them combine together to give you H, and H is sitting in this expansion rate, V is equal to HR, right? But H is also sitting in the denominator of this expression. Okay. So the dimming of light, to summarize, the dimming of light by a distant supernova is caused by the total energy density of the universe. How does this work in practice? Right. This works in the following way. So let me take 2 universes, right? So this is the popular universe. We'll come to this in greater detail, soon, which consists mostly of dark matter and dark energy, right? Now, dark matter is this omega m term. It's about a third. Dark energy is this term, 2/3. They add up to 1, all right? Because the universe is spatially flat. So now if you do this integral and you include the omega lambda term, this is what you get. Suppose and it is a very simple integral. It can be done analytically, right? I want to compute dl, and this is a redshift, right? So this is the picture, the graph that we get, right? This is the luminosity distance along the y-axis. This is the redshift. Now see the big difference, right? Suppose I set the dark energy component to be 0. This is the luminosity distance I get. It's the bold solid line. And if there's no dark matter, only dark energy, then this is the dashed line I get. So let's take a redshift 3, right? This value here you'll read is about 4, and the value here is about 12. So 12 divided by 4 is 3, and 3 squared is 9. All right, 3 squared is 9. So a distant object, say a quasar or a supernova at redshift 3, is 9 times fainter in a dark energy dominated universe than a matter dominated universe. This is really important, right? So there's a deceleration, there's acceleration, right? Now, notice that these curves for the different cosmologies actually fan out, right? They converge at redshifts much smaller than unity. And they converge to this beautiful relation, which is the Hubble expansion law, right? dl times h naught is cz. Cz can be interpreted as a velocity. So this is v is equal to h naught times r, crudely speaking. So this is very beautiful. So the point here is that if you want to see acceleration, you must go to higher redshifts. If you want to see new components in the universe, right, you must go to redshifts substantially more than, say, 0.3, right? And for that, you need to see very bright objects, and supernovae are those very bright objects which you want to see. So that was a little bit about supernovae and the luminosity distance, but how do you understand dark energy? How do you understand it deeply? Now, dark matter didn't pose this problem because you could understand dark matter in the framework of Newtonian gravity. Of course, the physics of dark matter is very deep, right? You need to understand it from the particle physics nitty-gritty, right? But to understand dark energy, you may need particle physics too. You need Einstein's theory of general relativity. So what's this theory? This theory is widely considered to be the most beautiful theory ever made by a single person. So now, let me remind you again that in Newtonian gravity, you've got the force law, F is equal to G m1 m2 over r squared. But it can be rewritten, right, as the Poisson equation, right? Phi is the gravitational potential, del square phi is equal to 4 pi g times rho, the density, right? So the density of matter is everything. It influences gravity. It creates phi, and grad phi is the force, right? Simple. But in GR, this is replaced by 10 equations, right? On the left-hand side is something called the Einstein tensor. And on the right-hand side is the energy momentum tensor, right? So this has been generalized to this, and this is this. And, John Archibald Wheeler, very profound scientist, summarized this in the following way, that matter tells space how to curve, and space tells matter how to move, because space curves matter, right? And matter is moving along geodesics in this curved space-time, right? But on the other hand, so space is telling matter how to move, but on the other hand, matter itself is curving space, right? So again, it's a jugalbandi, right? I enjoy these jugalbandis in science. So now, if you move to a universe that is homogeneous and isotropic, you realize that these 10 components can be simplified, right, into two components, one being the density and the pressure. So TIK assumes a diagonal form. And remarkably, Poisson equation changes again. It remains very simple, the Poisson equation. But instead of rho, you get a 3p term, rho plus 3p term. And this is profound. This is very profound because it is now telling you that pressure carries weight, that pressure can influence gravity. In other words, the dynamics of space-time is influenced not only by the density of matter, but also by its pressure. And if rho plus 3p becomes negative, right, then gravity becomes repulsive. Why? Because the right-hand side flip sign, okay? The right-hand flip sign becomes negative. It's just like you can imagine G flipping sign, right? The gravitational constant. What will happen? Everything will go apart, right? Nothing will be attracted, things will be repelled. That's why it's called cosmic repulsion, right? Rho plus 3p. Rho plus 3p, being less than 0 is also sometimes known as the violation of the strong energy condition. So in cosmology, you have these energy conditions, and one of them is the strong one, which is rho plus 3p is greater than or equal to 0. And here you violate it. You can violate it. You don't necessarily do. I mean, radiation does not violate it. Normal matter does not. But dark energy does. So let's look at this in the Newtonian framework again, because most of you, I realize, may not have done a course in GR. So I try to simplify this lecture. So the acceleration of a mass m, right, under the influence of a larger mass, capital M, is given by A, acceleration, minus gm over r squared. You all know this, right? M is nothing but the volume times the density, right? 4 by 3 pi r cubed rho times 4 by 3 r cubed times rho. Now, since m is always positive, it follows that the acceleration is negative, and that means that the object will always be attracted to m. This is simple observation. That's why we are all sitting in our offices and attached to the earth. Right? Now, Newton's theory, when it becomes Einstein's theory, you have the rho plus 3p term, right? And this active mass now changes to rho plus 3p. The same equation, but rho is replaced by rho plus 3p. So if this pressure is strongly negative, if this inequality is satisfied, then what you have is that this mass will be repelled by the larger mass. So m will feel a repulsive force, which will cause it to accelerate away from m instead of being attracted to it. Right? So this can be understood in a very simple quasi-Newtonian method. Now let's go back to the cosmological constant. Right? What is the cosmological constant? The cosmological constant is the simplest, one of the simplest forms of matter. Right? Mathematically simplest. Right? Why? Because the energy momentum tensor has this remarkably simple form. TIK is simply lambda times Kronecker delta ik. Nothing could be simpler. Now recall that the energy momentum tensor has this diagonal form, rho minus p minus p minus p being the pressure. I substituted, this is also diagonal, and I find that the pressure here is negative. It's minus rho, and it's equal to lambda over 8 by g. The density is lambda over 8 by g. So another important quantity in cosmology is that matter must satisfy the conservation equation, right? This is the covariant derivative of the energy momentum tensor. If you set it to 0, you get a conservation law. Right? This conservation law, you can see, is very simple, right? Density, as the universe expands, the density, some quantity must be conserved. Right? So what happens here is that if rho plus p is minus rho plus p is 0, and rho dot is 0, that means rho is a constant. That's why it's called the cosmological constant, right? Because it remains the same always. It's unchanging. Its value does not change with time. Now contrast this with what happens for pressureless matter. Suppose I have pressureless matter. This could be dark matter or it could be something else, right? I've set p to 0 here. Right? You can all integrate this equation, right? Rho dot is equal to minus 3 a dot by a. Integrated, you'll get log rho is equal to minus 3 log a. So rho goes like 1 over a cube. Right? So this is very important. If you have p, if you had radiation instead of matter, you would have p is equal to rho c squared by 3. And you will get rho is proportional to a to the power minus 4. Now this is very, very important because it tells us that cosmological constant contrasts to this behavior, right? The density in the cosmological constant remains constant as the universe evolves, while the density in other forms of matter radiation decreases. And that is why even if the cosmological constant is very tiny at early times, it can dominate the universe at late times. And our universe is very old. 13 billion years old. Okay, that's it. So here is a beautiful ellipse. It's slightly old, but it's very relevant. So the observers took 3 classes of objects, not objects, rather 3 kinds of observations. One of them was those of type supernovae, right? The famous type 1 is supernovae observations, and they found this broad confidence ellipse, right, which favors an accelerating universe, right? And then when they overlaid this with observations of baryon acoustic oscillations, essentially observations of gravitational clustering, and observations of the cosmic microwave background, this confidence ellipse shrank enormously. And the focal point of this ellipse, right, the center of it, corresponds to these numbers. Omega lambda is 2/3, and omega matter is 1/3. This is the key point here. So now the idea for a cosmological, for dark energy for an accelerating universe comes not only from supernovae, but also by combining different sets of observations. So now let's go back to the Einstein equations, right? So the Einstein equations in the presence of a cosmological constant become modified slightly. You get, actually Einstein put lambda in the left-hand side, and I'm taking it out here so that it looks like a form of matter. And when you write them down, simplify them in an FRW universe, I'm not going to derive all these equations, we don't have time. You get the following equation. The second derivative of A is the expansion factor. You can think of it as R, the radius of the universe or something like that, right? It tells us how the universe expands. The second derivative, which is the deceleration, is equal to minus 4 pi g by 3 A times the matter density. Matter density comes from here, plus lambda by 3 times A. Now let me make this transformation. A becomes R, just to make it more lucid. And then, I again substitute M as I did earlier for matter, right? This is pressureless matter. So I get the force, right, is minus gm over r square plus lambda by 3r. Remember, these signs are opposite. This is clear that cosmological constant gives rise to a repulsive force, whose value increases with distance. Okay, so you have an attractive force here and a repulsive force here. This is given by dark matter and baryons and radiation. This is given by dark energy. So what's happening now? Note that this equation, this is another way of writing it, since the density goes like 1 over a cube, right? I showed this earlier, right? The density drops like 1 over a cube. These two components look like the following. The minus sign has a 1 over a cube here. And so when A is very small, when the universe is young, this quantity dominates over this, which is a constant. And so the universe decelerates at early times and accelerates later. And in fact, at very late times, the acceleration becomes exponential, very rapid. And so you may ask, well, when did this sign change here, right? When did the universe just begin to accelerate? And the answer is, we don't know very precisely, but it appears to be at redshifts of about 0.6. And that is when the universe was about half its present size. That's when it began to accelerate. Not too far back in time, right? Not too far back in time. And those who like to solve complicated differential equations, well, try and solve this, right? The students might want to do it, right? It's a very nice exercise, and you can solve it exactly in terms of the sign hyperbolic function. And immediately you see that at early times, this gives rise to t to the power 2 over 3, which is a decelerating universe and an accelerating universe at late times. So another way of looking at it is the following, that here is the universe at early times, several billion years back. This is a cartoon I borrowed from the net. And dark matter is like a spring because it's kind of trying to decelerate the universe, right? All these are galaxies, right? And dark energy is this balloon. But with time, dark energy goes stronger and stronger and stronger. But all the time, dark matter is going in the opposite. So these two forces, are working in the opposite direction due to the difference in the signs here. All right. So now comes an interesting question that we find, as I told you earlier, that the dark energy density is roughly equal to twice the dark matter density. Right? Well, what's the reason for this? Right? Why couldn't it be a 10th or 10 times? And some people have called it, well, it's a cosmic coincidence. If you take two numbers, they could be very far apart from each other. But these two numbers are very close. So is this giving us a hint of something? We are still not sure. So now is the 1 crore rupee question: what is the cosmological constant? Right? It has these lovely properties, but what is it? Why put it in there? Who put it in there? Remarkably, it has an old history. Einstein proposed the cosmological constant way back in 1917, just 3 years after he discovered general relativity. Right? And the reason Einstein put it there was because he liked a static universe. Einstein was a firm believer in Mach's principle in those days. Right? Ernst Mach was a very influential philosopher, scientist, right? And he said that the laws of inertia are connected to the laws of matter in the distant universe, and for that you required a static universe. In 1917, nobody knew what the universe was like way beyond the galaxy, and so he put it in just to balance attraction exactly with repulsion. But even then, Einstein was very aware of what he had done, the enormity of what he had done. Right? Although these were his equations, he can do what he likes to them, right? And in a letter to Ehrenfest, Einstein wrote, "I have again perpetrated something relating to the theory of gravitation that might endanger me of being committed to a madhouse." Einstein was a very humble man. I mean, it's quite startling that he could make a statement like this. Right? He could have said, well, I think this is it. But he was aware this is something rather remarkable. The very same year, Wilhelm de Sitter presented vacuum solutions to this equation. Throw away matter. These are very beautiful solutions. They are known as the de Sitter spaces. Played an important role in cosmology. Few years later, a Russian scientist, Alexander Friedman, constructed a matter-dominated universe without lambda. It was an expanding universe. He threw this away, solved the equations, he got an expanding universe. Right? And in 1923, a year later, in a letter to Weil, Einstein says, well, if there is no quasi-static world, then away with the cosmological term. I mean, who cares? Who wants it? So Einstein, a very good physicist. He was not overtly fond of his own ideas, He said, you don't really need it. Around that time, possibly around that time, evidence for the expanding universe was also coming in, right? So he said, then away with the cosmological term. Much later, this is Gamow. George Gamow, he had a conversation with George Gamow Einstein, and this is what Gamow reports. Much later, when I was discussing cosmological problems with Einstein, he remarked that the introduction of the cosmological term was the biggest blunder of his life, right? So, Einstein perhaps was a little ashamed of introducing this term. What have we done now? What have we learned 100 years later is that what Einstein threw in his waste paper basket, the world has rescued it from there and put it in the centerpiece of cosmology, right? So Einstein, if he had been living, would have laughed, I'm sure. There's something he had discarded and he was actually ashamed of, right? Has become so important to cosmology. It shows how the minds of great men work. So here is roughly the wave of lambda. This is not a real wave. This is a historical wave, right? So we have Einstein discovered lambda. There was great interest in it, primarily because Einstein discovered it. But then, Hubble discovered expanding universe. Friedman discovered solutions, right, that led to expansion. And so interest in lambda faded. Then a remarkable thing happened in 1967. People started playing with quantum field theory, right? Not playing, but deeply discovering quantum field theory. And we realized that the vacuum has an energy. And the energy is like lambda. And then the third wave here connected with both inflation and dark energy. It appeared in 80 and it is continuing. And it is quite interesting that this wave of lambda, this historical wave, actually coincides with another very interesting wave, again, in the history of science, a wave in the history of science, and that is a wave of extra dimensions. Because in 1921, Kaluza suggested that there could be a fifth dimension, but you don't see it, so it could be curled up. It could be curled up and very small, just like, if you curl a cylinder and make it tiny, it can eventually become the size of a hair. Again, in the 70s and 80s, around this time, modern Kaluza-Klein theory was born. And people tried to apply these ideas, higher dimensional ideas, to non-abelian gauge fields. Right? And now these ideas have been taken further by brain world models, extra dimensions, string theory. Many of these objects live in extra dimensions. That's quite interesting. These are just like historical parallel. So let's go to the second wave of lambda, right? 1967. Now, Pauli had already in the 30s shown that there is a consequence of quantum field theory is the existence of vacuum energy, and that it can be large. Zeldovich in 1968 is a very nice, very influential article, The Cosmological Constant and the Theory of Elementary Particles. Now, Zeldovich was a very versatile scientist. He started his career in chemistry. He had never been to college. He was, just straight out of 10th class. He was very, very clever person. He first became a lab assistant, right, in chemistry. He was noted by a great chemist, Yoff, brought to Moscow, did amazing work, right? Became a nuclear physicist, particle physicist, then cosmologist. So this is the time when he was just moving to cosmology, and he realized that the vacuum, right, is seething with activity, and the vacuum energy has properties very similar to those of a cosmological constant. And in this paper, Zeldovich actually wrote towards the end that the genie, the cosmological constant, has been let out of the bottle, and it is no longer possible to force it back in. This is a very present statement. It was made in 68 because the cosmological constant made a big impact, not only on physics, but on cosmology in 1980 with the discovery of the inflationary universe, which has an equation of state P being very negative, and again in 2000 when the discovery of cosmic acceleration took place. So what's the bottom line here? This is for kind of your BSc, MSc level students. So if the vacuum has energy, then it should obviously be Lorentz invariant. So those of you who are familiar with these coordinate transformations, well, let's go to a boosted frame, right? Moving with respect to the original frame. Write your prime components of the energy momentum tensor. They'll take this form, right? Then substitute this diagonal form for the energy momentum tensor. And lo and behold, you will find that the prime frame also has this form. This demonstrates that P equal to minus rho is Lorentz invariant. Of course, just the energy momentum tensor TIK, lambda GIK itself, if you look at it, you realize it's Lorentz invariant. But this is a nice exercise if you want to do it. So what is the vacuum? I always love this picture of the vacuum given by Feynman, right? That there are these virtual particle-antiparticle pairs forever being created and being born, right? And there, of course, they always satisfy this inequality. And these pairs, the reality of these pairs has been measured in the Casimir effect. Some of you must be familiar with it, right? It's a fantastic effect. It confirms the existence of vacuum fluctuations, And so you find that the vacuum is actually seething by activity. And it has this equation of state. Now, let's go back to this a little bit, right? Again, this is kind of quantum mechanics, physics, right? Let's go back to your harmonic oscillator. Now, if it's a classical oscillator, it will oscillate, damp out, and sit here. Right? But if it's a quantum oscillator, you quantize it, right? And you quantize it into energy levels, and you realize that the lowest energy level, the ground state, has energy. Right? It's half h omega. Okay. So, you can always quantize your electromagnetic field, say, right, into a bunch of harmonic oscillators. There's a beautiful chapter in Landau-Lifshitz on this, right? How you can do this, right? Normal mode decomposition, it's called, right? And when you do it, you find that this energy, now let's call it the energy momentum tensor, T naught naught, because it's a vacuum expectation value, is proportional to half h omega. That's it. You can't make the oscillator come to rest. Right? It's always having that 0 point activity. So now when you actually do this integral, right, this depends on the mass of the field and on its spin, right? But if you just look at this quantity, you realize that there could be trouble. Why? Because suppose I set, if I set the mass to 0, or if I take the momentum to be very large, right, okay, you realize this integral diverges. And it diverges as k to the power 4. This is known as an ultraviolet divergence. So the vacuum state has infinite energy. Right? This is well known. This is known as the cosmological constant problem. So you might say, well, you're not allowed to go to infinite energies because who knows what physics is like at infinite energy. So let's take a sensible energy scale. Let's take the Planck scale. Now the Planck scale is made up of three fundamental constants, h, c, and g, right? Okay. And the Planck mass has a value of 10 to the minus 5 grams. So when you substitute this in here, out here in the upper end of this integral, you get this enormous density, 10 to the power 93 grams per centimeter. Remember, the density of water is 1 gram per centimeter. Now compare it with what is observed. The observations is 10 to the power minus 30 grams per centimeter. Right? There's a mismatch of 1 part in 10 to the power 123. Okay. So how does one account for this enormous mismatch? How does one account for a tiny value of lambda? Now, in the 70s, it appeared that supersymmetry might come to our rescue on this point. Why? Because bosons and fermions contribute with opposite signs to the vacuum energy. And so if there's a perfect symmetry between bosons and fermions, the vacuum energy would just cancel. Unfortunately, if supersymmetry does exist, it's controversial, but if it did exist, it would be broken at the low temperatures prevailing in the universe today. And then the typical temperature you would have to substitute in that integral would be the supersymmetry scale, SUSY scale, right? And that is enormous, right? And that would give a value of the vacuum expectation not as large as the Planck value, but 60 orders of magnitude difference here also. So supersymmetry can't help. This is our current understanding is summarized in this transparency. You have the observed value of the vacuum energy, 10 to the power minus 30 grams per centimeter cube. Formal field theory gives you infinity. Quantum gravity might drop it to 10 to the power 90. Supersymmetry can drop it further. Now, it's very interesting that the Higgs potential on its own gives a negative value for that, large negative. You have to renormalize it to raise it up to 0. And there are other sources as well, right? So this leads to the cosmological constant problem. And those of you who are interested further in this, I would like to refer to you to a very beautiful review paper by Steven Weinberg, several decades ago. The references here, Reviews of Modern Physics. And Weinberg starts with this quotation from this nice poem, right? I'll read it out to you. As I was going up the stair, I met a man who wasn't there. He wasn't there again today. I wish he'd stayed away. So, it's like you're in a dark room and you believe there's a black cat and you can't see it. So, lambda is supposed to be large. Why is it 0? This was a question being asked before 1998. Right? See, you know why the photon has 0 mass? Because of the U1 gauge symmetry. Right? But there is no such symmetry for lambda. Right? And everything is telling us that it should be large. So this is the cosmological constant problem. And whatever you did, it was very difficult to resolve this issue. But I think the situation today has got slightly worse because it's actually, you discovered that there's dark energy and it's tiny. So you're not asking why it's 0, you're asking why it's very, very small. Right? Anyway. Now, the cosmological constant has many attractive features. As I told you, its equation of state is Lorentz invariant. It's a very beautiful quantity, but it may encounter a fine-tuning problem. What is this fine-tuning problem? Look at it in the framework of, not particle physics, but cosmology. As I told you earlier, the density in all forms of matter drops off as the universe expands. Right? 1 over a cube for matter, 1 over a4 for radiation. Today, these two quantities are roughly equal. Extrapolated back in time, near the Big Bang. Right? At the electroweak scale, this imbalance, the ratio of lambda to matter, was 1 part in 10 to the power 44. This is just the electroweak scale. Right? If I go to the Planck scale, if you go right all the way to the Big Bang, this imbalance is enormous because the matter density goes through the roof and lambda stays the same. So the point here is the following, right? Why has lambda got this value? Now, some people appeal to anthropic arguments also. They are also quite interesting, You see, if lambda had been very large, say it had been 10 times its value, it's a repulsive force. it would have prevented galaxies from forming, right? And so there would be no conscious observers like us to see lambda. That's an interesting point, right? Okay. Whereas if lambda had been very negative, it would have been a super attractive force, right? And what would have happened is that the universe would have collapsed long ago because lambda would have had negative density. And negative density always makes the universe collapse. So again, the universe would have not been 10 billion years old, but just maybe 500 million years old or a few million years old. Again, galaxies couldn't have had time to form, and there would be no intelligent life and no cosmologists worrying about lambda. So there is just a small window here that is actually allowed by anthropic principles, right, where intelligent observers can exist. So this becomes important in the context of the multiverse and other such ideas, right? But I'll not talk about those ideas here. The question is that, well, are the initial conditions here fine-tuned? Because, after all, each theory in physics has initial conditions plus equations of motion, right? The equations of motion here are the Einstein equations. Well, but what were the initial conditions, right? Did they need such fine-tuning? So people worried about this, and this dilemma of the cosmological constant remaining constant prompted people to look for dynamical models of dark energy, models in which dark energy evolved with time. So let me motivate a couple of these models. Now, remember, again, for those of you who are at your BSc level, remember that you are all familiar with the Lagrangian for a particle, right? Point particle. This simple Landau-Lifshitz volume 1 mechanics, right? It's kinetic energy half mv squared minus the potential energy. Right? Now you can generalize it to something called a scalar field. The Higgs is a scalar field. Right? So these are fields. In physics, they usually talk about fields. Right? The electromagnetic field is a field, but it is a vector field. Right? So here we have a scalar field. Right? The simplest field is a scalar field. And you generalize it, instead of r, you have phi, and phi depends on all the coordinates and on time. So you have the kinetic term half phi dot square minus the potential term v of phi. This is called a scalar field Lagrangian. Now, if you say, well, what about, this is the classical Lagrangian for a point particle, what about the relativistic Lagrangian? Right? Okay, can you generalize that? And the answer is certainly, you can do that too. Right? Again, instead of v, there's no potential here, remember, but you have a velocity. So, substitute it, right? Again, the coordinate becomes phi, and you have something known as the Shaplevian gas. It's a very interesting quantity, very interesting. So let's begin with the scalar field Lagrangian. Right? So the point is, try to model dark energy using this scalar field. Right? So from a Lagrangian, you can construct the energy momentum tensor. It's easy to do. The density has this form, phi dot square plus v. Pressure has phi dot square minus v. So immediately you see that the pressure can turn negative. Beautiful. This is what you want. You want the pressure to be negative. The scalar field does that for you. Great. Now what happens is that if this potential is sufficiently steep, if it satisfies the same quality, in particularly for an exponential potential, you find that the scalar field behaves like a tracker. What does that mean? That means that the density of the scalar field to the total density of matter remains constant as the universe evolves. So you can have the scalar field starting from a very large value and ending up to a small value. And all the time it's tracking. So this alleviates the initial conditions problem. If this is dark energy, it can do this. But I'm sure you've noticed a flaw here, because this form of dark energy never dominates the universe at late times. So it can never make the universe accelerate. Fine. So this may be an approximation to the potential, right? It doesn't have to be the full potential. So the point is that you have this very nice relationship, right? That if the potential satisfies that inequality, right, then all trajectories approach a common evolutionary path from a wide range of initial conditions. That's some kind of an attractors. So take an example of this potential, right? This was proposed by Rathra and Peebles back in 1988. Now you find that the density, the ratio of the densities actually grows with time, right? It becomes larger and larger as time evolves. Okay. And so you can start out with quintessence energy. This is sometimes known as quintessence. Quintessence is the fifth element, right? And it's large to begin with. It's following radiation, then it's following matter, and it dominates today. Beautiful. So the initial conditions problem, which arose for cosmological constant, is largely alleviated for these models of dark energy, dynamical models. Let's turn to Chaplygin gas, right? Chaplygin gas has this Lagrangian, right? For those of you who are scared of this Lagrangian, don't worry. The important thing is that the pressure again is negative, and it's minus the constant by rho, the density. Beautiful. This is what you want, negative pressure. Now, if you plug this into the conservation equation, right, dE is equal to minus PdV, this holds in GR2, and you integrate it, you find that the density is equal to the square root of a constant, A plus B, another constant divided by A to the power 6. So imagine the universe expanding, A was very tiny at early times. That means the density fell off like 1 over A cube at early times, just like matter. And today, it became a constant, just like cosmological constant. So this was realized in a very nice paper by these authors in 2001, very soon after dark energy was discovered, that, hey, this Lagrangian gives you everything, right? Behaves like both dark matter at early times and like dark energy at late times. So perhaps you can use it to unify dark matter and dark energy. And I read this paper, I was extremely excited. I said, man, they found it, right? I mean, what could be better? Simple Lagrangian explaining 96% of the universe. Unfortunately, this doesn't work because subsequently people analyzed this model further and they found that, the velocity of sound actually grows very rapidly with time, and it does not give a satisfactory model of structure formation. So it gives a good model of the background universe, but not of clustering of galaxies. There's yet another way of constructing dark energy from and dark matter, and that is by a very simple scalar field. Just take this scalar field, 5 to the power 2p. Now this has a minimum, right? And when the scalar field hits a minimum, it will begin to oscillate. Then you can apply a virial type of equation. W is mean value of W is p minus 1 over p plus 1, right? P is this exponent. Put p equal to 1, you get 0 here. That's dark matter. It has pressure. It is pressureless, right? And set p to smaller values, you get W less than minus. That's dark energy, right? So this potential corresponds to dark matter. This potential corresponds to dark energy, right? This is pointed out long ago in a paper which I wrote. So now I have focused so far on one way of making the universe accelerate, and that is modifying the matter sector of the theory. But there are actually two ways to do this. And the second way is to modify the gravity sector. And actually Einstein proceeded in 1917 along this direction because he introduced lambda into the left-hand side. And nowadays people have worked extensively on this, and they find that there are other models of dark energy. They can be geometrical models, extra-dimensional models, and other FFR theories too. So let's come to this sector, this way of modifying gravity. So cosmic acceleration modified gravity. You see, in the presence of matter, you need matter to violate the strong energy condition, right? Okay. But if you don't have matter, you can still do it. And this was pointed out by Starabinsky way back in 1980, right? He showed that, well, if I introduce an R-square term to my Einstein-Hilbert action, then this quantity leads to fourth order equations for gravity. The box R term appears in the equation of motion. And this gives rise to cosmic acceleration. Starabinsky was not trying to explain dark energy. Dark energy was not there at that time. He arrived at inflation, right? Okay, which now bears his name, Starabinsky inflation, right? Or R-squared inflation. And if you actually look at the latest CMB maps, right, of something called the tensor to scalar ratio, plotted versus the primordial tilt, right? These are quantities that play a very key role. The fluctuations arising from inflation. You find that observations give you this kind of contours. These are the contours, error contours, right? And there are these upper bounds, and Starabinsky inflation sits bang in the center. So it agrees very well with observations. Right? So what I'm drawing your attention to is the following fact, that you can have acceleration without matter, simply by modifying the Einstein-Hilbert action. In other words, modify the gravity sector of the theory. Now, when dark energy was discovered, people said, hey, wait a minute, if R square gives rise to early acceleration, maybe 1 over R will give rise to late time acceleration. No, why not? And it actually does. If you solve this equation, it actually does. You solve this action right. But unfortunately, this model develops strong instabilities. Right? It kind of breaks down completely. An instability-free models have been produced by generalizing this to an f of R theory, right? It's important that this inequality be satisfied, and it can easily be done if you have a more complicated form for f of R, right? This kind of ansatz, and this was developed by Hu and Sawicki, and later other people also. Some of the references are given here. Okay, a completely different way, a novel way of sourcing cosmic acceleration is to stay with the Einstein-Hilbert action, but live in extra dimensions. Right? Now, as I pointed out to you earlier, the idea of an extra dimension is really old. It goes back to the early work of Kaluza and Klein. And they showed that the U1 gauge symmetry of electromagnetism could be associated simply with a compact fifth dimension. Right? So here you've got this fifth dimension, right? Here's a mathematical view. You've got a fifth dimension. And here you just curl it up, right? You curl it up. So it becomes compact. And here is time flowing, here is space flowing. And you've got a compact fifth dimension. Of course, the fifth dimension has to be really tiny, so you don't observe it through your microscope. Right? Now what you do is you write the Einstein-Hilbert action in 5D, in 5 dimensions. Here it is. And then in 4 dimensions, when you integrate over the extra y coordinate, you get GR plus electromagnetic Lagrangian. Right? Beautiful. It just falls out. And a dilaton. So this result was so beautiful. Einstein also loved it. Right? He actually wanted to unify the forces. This is something he was devoted to for the last few decades of his life. How do you unify the fundamental forces? Maybe they are all geometrical in nature. Right? Unfortunately, he didn't succeed, but those ideas are still around. Right? So this is the beautiful idea of compactification. Right? Later on, people generalized it to more than one extra dimension, 3, 4, 5, even more. So now, a certain change in the paradigm occurred about 1998, around the same time as cosmic acceleration was discovered, right? And some scientists said, well, maybe the extra dimension need not be small, maybe it can be large, right? It can be large, but the standard model fields are confined to a subdimension, right? To 3 plus 1 dimensions, right? But the loops, so the gravitons can escape into the bulk. So the idea was that there is a bulk space-time and there is a brane. And our universe, 3-dimensional universe, is like a membrane embedded in a higher dimensional bulk space-time. Okay. Now, if you do this and you change the Einstein equations, you find that the conventional expansion can be modified either at early times or at late times. This is very profound consequences if these models actually work. Right? Another way of looking at it is that our universe, there's a bulk extra dimension, this is our brain. So, an early idea of this, right, was the wormhole, right? You've got a wormhole, connecting 2 different regions of space, and you can look at this as, as a strip of paper which you bend, right, and then you stick them together here, right? There are 2 ways of traversing these regions if you want to go from here to here. One is either you go all this long normal route, long way, or you go through the wormhole. Right? It's also known as the Einstein-Rosen bridge. And here's a more artistic picture of the same thing, right? It's very beautiful, right? That you have a bulk, higher dimensional geometry, and you have the brane, right? So most of us live on the brane. We have to travel these long regions to go from one place to another. But who knows, if there is a wormhole, you might go through it. And those of you who have seen this movie Interstellar, right? There are very nice graphic visuals about this person trying to get through the bulk, right? And very interesting things that happen here. Because you can have closed time like loops and stuff like that. So this is just a visualization of what an extra dimension might actually look like. And we are observers, and we are living on this brain world. So now, the mathematical theory of brain worlds is very beautiful, right? In fact, if you have now the action, you generalize the action to the extra dimension, right? So you will have now another constant appearing, and that is a 5-dimensional Planck mass, or you can say equivalently the 5-dimensional gravitational constant. Right? And if you write the Hubble parameter, it has this very interesting form, right? So you got the matter term, and a new constant appears here. And this constant is the ratio of these two fundamental constants. And it's quite interesting that if you take values, which are natural in the sense, m is 100 MeV, and this is the Planck scale, then the value of L becomes of the order of the Hubble scale today, right? And this should be compared with the expansion law in normal lambda CDM cosmology. Very similar, very similar. The difference is this term here, right? So this extra dimension behaves just like an accelerating term, behaves just like dark energy. Lambda CDM has one extra parameter lambda. Here also there is just one extra parameter which controls late time acceleration. So you do get acceleration without dark energy, right? Just by making your model a 5th dimensional model, right? Unfortunately, this model suggested by Dwali, Gadavadze, and Porati ran into ghosts. Right? This was the famous DGP model, had ghosts, and so it doesn't work really at the fundamental level. But brain world models without ghosts can be constructed. We constructed them with my collaborator Yuri Shtanov back in 2002. And a key feature of some of these models, as dark energy can have a very strong negative pressure. This is sometimes known as phantom dark energy. This is a key characteristic of these surviving brain world models. So now, to move away from extra dimensions, or rather move away from this subject a little bit, from dark energy, there is a very intriguing issue, and that is that you see the universe appears to accelerate twice. One is at very early times in the form of inflation, and the other is today. Right? So what is going on here? Right? The universe accelerating, then it decelerates for a long, long time, several billion years, and then begins to accelerate again. Maybe these two quantities are related. We don't know. Right? Okay. So let's come to inflation. What is the early universe? So you see, you have again the exponential expansion law, right? Okay. So you have something very close to dark energy. Let's call it early dark energy, right? And it is driving a very rapid expansion in the universe, right? But inflation unfortunately runs into a Big Bang singularity. I'll talk about that as well. So inflation is involves an exponential stretching of all distance scales. This is a cartoon which I made, right? So if you start off with inflation having a very, inflationary patch having a tiny value, say the Planck scale, 10 to the minus 33 centimeters, very, very rapidly, this will get stretched to a centimeter, which is a macroscopic scale. And then normal decelerated expansion will take it up to the present scale. Right? And the important thing is that, so a single burst of inflation is sufficient to make the universe large and spatially flat, which is observed. And inflation can stretch very microscopic scales to macroscopic scales in a very short burst of time. Right? This takes place in just 10 to the minus 33 seconds. Right? And so this is, if you like to look at it like this, the equation is now very simple. It's r double dot is lambda by 3r. So you're just accelerating very rapidly. And this is exponential. Now the problem here is that some people proved a theorem that inflation cannot be extended forever in the past. It has to begin at some point. And what happened before that, we don't know. So maybe the universe ran into a singularity. And Hubble's law tells you clearly it will, right? Because h squared is proportional to rho. As rho increases, so does the expansion rate. So if the density goes to infinity, h goes to infinity. Now, why I'm drawing your attention to this is because extra dimensions could cure this singularity. As I told you, extra dimensions can play an important role at early and late times. Late times you've already seen, right? It can give rise to dark energy. At early times, it's very interesting that if your extra dimension is time-like, the universe has another time-like direction, right? In addition to the normal time, then this you have a minus time entering here, right? And so at some time when rho is very large, right, when rho is equal to some constant rho c, h goes to 0. H goes to 0 means the universe stops expanding, right? So there's no singularity. Now, this same result was obtained by us and also just a few years later by Abhay Ashtekar and his group using completely different physics. Their group used loop quantum cosmology, a very nice direction towards quantizing gravity. So this is what happens. Instead of a big bang, you have a big bounce, right? The universe started here, bounced, and became large, and galaxies developed. And so in such models, right, you will have an oscillatory universe which keeps getting larger with time. In other words, you can get a cyclic cosmology, provided you have terms like this. So now I come to the final part of my talk, and that is reconstructing dark energy. What is reconstructing dark energy? The point is that so far we have numerous, I'm moving back now to dark energy from a little bit on inflation, right? Or the early universe, right? So very many dark energy models have been constructed to, say, account for an accelerating universe. The simplest is, of course, the cosmological constant, but you can also have W constant and not equal to -1. Cosmological constant is just a subclass here. You can have quintessence models in which W varies with time, scalar field models, Chaplygin gas, phantom dark energy, W is strongly negative, oscillating dark energy, models with interactions between dark energy, and so on and so on and so on and so on. So now, 20 years after dark energy was discovered, you have two choices. Right? Either you go and test your favorite model against observations, which is a very valid and nice thing to do, or you try to reconstruct the properties of dark energy from observations in a model-independent manner, right? And this approach is also very important for understanding the accelerating universe because you don't assume any of these models, right? Okay. So clearly the cosmological constant stands out because of its elegance and simplicity. It may or may not be the answer, but it's clearly a very attractive idea. So as a first step, let's find tests which could falsify the cosmological constant hypothesis. These are known as null tests for lambda. Let's see how you can devise these null tests. So let's go back. Let's go back to the fundamental quantity in cosmology, the expansion factor. Now, all of you know, we observe it at some time t0, but it can be expanded back in time. If t0 is the present time, let's expand it in a Taylor series. Now, the first term is the derivative, first derivative, second term is the second derivative, and so on. Now, in 1970, when this field of observational cosmology was just beginning, right? Alan Sandage described observational cosmology as being a search for two numbers. Essentially, a search for two numbers. The first number is the famous Hubble constant, H0, and the second is deceleration parameter. And these two are fundamental, right? Remember, in those days, in fact, when I was in grad school, right, people said H0 is 50, and some other people said H0 is 100. And there was a big fight between these two groups. Right? Is it 50? Is it 100? Is it 50? Is it 100? Because, the error bars being quoted were ridiculously small. Right? H0 is 50 plus minus 500 is H0 is 100 plus minus some 10 or something. Right? Now we know it's neither of those. It's somewhere in the middle. It's about 70. Right? And now the precise value becomes important. But also Q0, right? In those days, you didn't know what is Q0. It could be from -1 to 0.5, right? It could be decelerating or acceleration. So you had to focus on these two numbers, kind of make them more and more accurate, more precise. But now we have moved on beyond 1970, right? We're 50 years, half a century ahead. And we are getting to know the observations extremely accurately, especially in the next decade. So let's define a third number, the triple derivative of A. This is a dimensionless quantity, A triple dot over AHQ. Very remarkably, if you determine this in a lambda CDM universe, it's equal to 1. It does not evolve with time. Like lambda, it stays the same always. Right? In any other dark energy model, R is not 1. If you define a second number, can be defined quite remarkably also, right? It's R minus 1 divided by 3 times Q minus half. Q is just the deceleration parameter. And now you find, lo and behold, S is 0 only in cosmological constant. In all of the models, S is not 0. So we've discovered a null diagnostics for lambda term. Since these two, which we call the state finders, they are equal 1 and 0 only for the cosmological constant. So you have observations, and I find that this number is close to 1, but this number is not, over the stories or for lambda. So let us see what dark energy models have to say about these numbers. If you do this, you find that, well, it's very easy to do, just take your favorite dark energy model, plot it here. So standard cold dark matter sits here without lambda. Lambda sits right in the center here, right? Lambda CDM means cosmological constant, lambda plus cold dark matter, right? And other models are way away, right? So here is your quintessence model, right? It is evolving depending on the value of alpha from here and converging to lambda. So lambda is a fixed point. The universe in these models evolves towards it at late times. Right? The Shaplegian gas works in exactly the opposite direction. Right? So if you look at it in the state finder plane, these two models are completely complementary to each other. Very beautiful, right? The state finder has just separated cosmological models. Quintessence models in which W is a constant follow a totally different evolutionary path. So in some sense, the state finder diagnostic provides a fingerprint of dark energy. And you can easily distinguish cosmological constant from the models. So right now, with the current state of observations, it's hard to get the third derivative of A, right? It's hard, right? Second derivative is still possible, third derivative is hard, but observational data expected during the coming decade from beautiful experiments, including DAISY, Dark Energy Survey, Euclid, Square Kilometer Array, will definitely help us to understand whether or not dark energy is Einstein's cosmological constant or whether it is something much more exotic. Now, what does dark energy do to the cosmic web? After all, it's 2/3 of the universe is in dark energy. What does it do? And this is a very important question because the dark energy also affects the cosmic web, the assembly of structure in the universe, profoundly. Because remember what is happening here, right? Dark energy is a force of cosmic repulsion. It is trying to repel galaxies away. Gravity is trying to attract galaxies. So gravity is trying to assemble the cosmic web. Dark energy is trying to stop that assembly. So it's trying to slow down that assembly. So if you look at an n-body simulation of a lambda CDM cosmology, you find the following. You already see superclusters already forming here. There's a beautiful void forming. Here's a beautiful cluster. This is a redshift of 1. And this is redshift 0. And actually, you see that there's not that much difference between redshift 0 and 1, right? This little supercluster was already in place at redshift of 1, right? This cluster was already there. So the assembly of structures is kind of frozen in time, right? Gets frozen in time. But look what happens if you throw away lambda, right? If you just have dark matter, boom, it just goes on, right? Because it doesn't know about dark energy. Clustering continues and continues and continues forever. And the reason this happens is very easy to see mathematically because the clustering equation, delta here is the density contrast, right? Rho minus the mean value, the density minus the mean value divided by the mean value. It's a dimensionless quantity, right? This quantity satisfies this equation, which is like a damped oscillator equation, right? Only the frequency in an oscillator, this would be W squared. Here is W squared to the minus sign. So there's an instability that is known as gravitational instability. You know that an oscillator with an imaginary frequency is unstable, right? But in addition, so this instability is very important, right? This is known as the Jeans instability. It gives rise to structure. But the friction term is caused by expansion of the universe. And dark energy is aiding that expansion because it is sitting here. All right. It is sitting right here. And so it's acting like a damping term. And because of that, the cosmic web slowly begins to freeze over time. So in other words, the large-scale structure of the universe can also be probed used to probe cosmology. And very briefly, I mentioned that the density perturbations grow at a slower rate in these quintessence models and at a much faster rate in the brain world models compared with lambda CDM. So the different dark energy models affect the assembly of structure in different ways. And so this is going to be a very beautiful potential test of the nature of dark energy. And so I think, to summarize, that big breakthroughs await us. More than close to 1 billion galaxy redshifts will be known very soon on the big surveys coming up, and they will help us. Thousands of high redshift supernovae will also be known. Epoch of recombination will be known, and so you'll really get some, I'm sure, quite exciting and very informative information about the nature of dark energy. So before I end, I want to summarize my talk, and I'll summarize it by listing these 5 open questions for dark energy. These are my questions. These are questions I ask myself. These are personal questions. The first question is dark energy a cosmological constant, or is it something else? The second question, does general relativity need to be extended to accommodate cosmic acceleration? That is modified gravity. You need to modify gravity. Right? The third, is late time acceleration related to early time acceleration? In other words, is dark energy related to inflation? 4, why is the density in dark matter and dark energy almost the same? Is this simply a cosmic coincidence? This may be related to the 5th question. Are dark matter and dark energy related? Perhaps. And in fact, in a very exciting recent work, which I did with Anjan Sen, first in Jamia, and then my student Swagat Mishra, we showed that a simple generalization of the canonical scalar field Lagrangian to this form can lead to a possible unification between dark matter and dark energy. Here, the kinetic term plays the role of dark matter, and the potential term plays the role of dark energy. This work is still continuing. We are still investigating whether indeed this will work at the perturbative level. So, and this is the important issue I mentioned, are these 2 regions related? So finally, back to Einstein, the discoverer of lambda. And Einstein said a beautiful statement, made a beautiful statement. The significant problems we have cannot be solved at the same level of thinking with which we created them. Right? The significant problems we have cannot be solved at the same level of thinking at which they were created. And I think this may be true for dark energy also. Thank you very much. I'm done.
Hi, we have some questions to answer. So I would ask. So there are several questions, and some people have trouble with their speaker, their mic. So I will ask them. But first, I would request Yashodhan Joshi to ask his question.
Hello, sir.
Hello.
Sir, I wanted to ask that you showed that graph where there was
Can you
initially...
speak louder? Can you speak louder, please?
Hello, sir.
Yes.
Can you hear me?
Yes, I can hear you. Yes.
Okay. Sir, in the graph that you showed where there was initially inflation, then a deceleration and acceleration again,
Yes.
Can it be a periodic cycle where inflation and acceleration are the same thing, but the magnitude is dependent on density of matter at that time, and then it will continue to be periodic?
Right. This is the picture, right?
Yes, sir.
Yeah. Well, I don't know really. This is an intriguing question. You see, we believe that inflation, actually, what happened here was that at this time there was no matter, right? All the energy of the universe was in this inflaton field. But then the inflaton lost its energy and gave it up to matter, right? But maybe a little bit, a residue remained, which became dark energy today. So now if this dominates, then it will again have to give its energy again to matter, right? That's what you are suggesting, right? And then again, the universe, we don't know. You have to come up with interesting models of that kind. But yes, that is an intriguing question. Thank you.
Yes, sir.
So there are some more questions. First question is, I think this is already answered though. How do the evolution of dark energy with time becomes more powerful to dominate it at late times? and dominate it over dark matter?
Oh, that is because, let me see where this is, right? This is because the pressure can become negative, you see. So remember one thing, right? That whether a quantity dominates or not at late times depends on its pressure. Right? If it's positive, then it's subdominant. Now what happens here is that at early times, the potential is very steep. So phi dot square dominates, right? It's a very steep potential. The potential, the field is falling very rapidly down its exponential potential. Right? So the pressure is positive. Right? But at late times, the potential becomes somewhat like this function, right? This is exponential function. It becomes flat, and so the potential begins to dominate. It doesn't happen for exponential, but that's what happens, right? And so at late times, the pressure turns negative. And that's when the dark energy starts to dominate for these models. I hope. Does that answer your question?
I think this is what he asked. So the next question is, can there be negative energy density which could explain dark energy?
No. You see, a negative energy density does just the opposite, right? You need a positive energy density and a negative pressure. Because your rho plus 3p has to be negative. So you might think that, okay, I make rho negative, but that will, you see, the Hubble parameter, h square, right? Where does that transparency, right? Somewhere here. Yeah, h square is the sum of densities. So if this density is negative, and it's like a cosmological constant, it's a negative cosmological constant, then remember it will dominate at late times for sure, but with a negative sign. So it will cancel all these energies and h will go to 0. So universe will stop expanding, it will contract, right? It will collapse. So a negative cosmological constant is not that great for cosmology.
Now, another question is, when we curl one extra dimension, we might get dark energy. Can there be more extra dimensions which could be curled?
Yes, actually, the idea of curling one extra dimension was to give electromagnetism. That was the original idea of Kaluza and Klein, right? To get dark energy, you need not have it curled. It can be very, or curled and very large, right? That's the brain world scenario. Now, in most of these scenarios, in fact, if you look at the formulation of string theory or M theory, right, this formulation occurs in higher dimension, right? So then you ask, where are the extra dimensions? And they are compactified. So certainly most models, the brain world models are actually toy models. They illustrate something, but realistic models will have more than one extra dimension, certainly. Some of them could be compactified, some of them could be infinite. We don't know yet. Depends on your mathematical construction of the theory. Yes.
Two more questions. First question is, just like we are looking for dark matter directly by direct detection experiments under Earth, can we also look for dark energy through similar experiments?
If this was true, it would be lovely. I would welcome that because that's the way physics works, right? You want to detect something, but we don't know what is dark energy. Right? You see, we don't have anything that has negative pressure. We don't have an example of that in the laboratory, right? And no particle has that property, right? See, dark matter, we are lucky in a sense because we model it on neutrons, protons, but it's exotic. It's a neutrino, right? But even neutrinos have positive pressure, right? Everything has positive pressure, right? So we have no clue what is dark energy, and so we don't know how to look for it. But if we could, that would be great. For instance, if it interacted weakly with electromagnetism, that would be fantastic. That would be very, very nice, So it's all about model building right now. You build a model that is consistent with observations, introduce a interaction Lagrangian with the standard model fields. Please, there is your observation, there is your detection. Because it has to interact with the standard model fields in order to be directly observable. So you've got to build that interaction into the theory. That is in fact done for inflation, because that is how the inflaton decays into the standard model fields. Right? Otherwise, if the inflaton was like dark energy, forget it. There would be no universe today, right? Because it would not decay, right? All the energy would remain stored in the inflaton, right? In the early universe. So maybe dark energy is like that, And your question is very appropriate. Maybe it also, like the inflaton, interacts very weakly with standard model fields. And then certainly you should be able to detect it by constructing, sensitive experiments, suitable experiments.
One student has asked if there is any interaction between dark matter and dark energy.
Well, many models have been written on this, right? There are scores of models on interacting dark matter and dark energy. And I didn't have time to talk about it, but yes, there are interesting models. Yeah.
So that many questions for today. Let's thank Varun for this great 2 lectures.
Thank you very much for listening.